Hello and welcome to another edition of the Moving Iron Podcast. This podcast is proudly provided by Axon, helping dealers move more iron for almost 100 years. Find out more at axontire.com. Axon was started almost 100 years ago out of a passion for keeping agriculture moving. It's that same passion that drives them today. With a vision for a better experience for both farmer and dealer, they set out to create a better way to move more iron. When you partner with Axon, you get immediate access to a full range of products and solutions designed to meet the complex needs of today's grower. Axon carries all major brands and sizes of tires, wheels, and tracks. From custom colors and sizes to fully customized wheels, you can have the solution for virtually any problem today's farmer is trying to solve. To find more or become an Axon dealer, please visit axontire.com.
Moving higher in the 21st century. Hard-working people working hard for you and me. Moving higher, time and time again. Through the years you'll find us here. Moving higher.
Hello and welcome to this special edition of the Moving Iron Podcast. This is a two-part series that Shawn Hackett and I did where we interviewed Dr. Valentina Zharkova. And for those of you that don't know who Dr. Zharkova is, she is a brilliant mathematician, astrophysicist. She has a PhD in applied mathematics and solar theory. She's been studying the sun and the effects that the sun has on the solar system as well as Earth for the better part of 40 years. She has a very, very distinct background, and she has several peer-reviewed periodicals, papers, and been published many times in various industry magazines and articles and periodicals and those kind of things. So Dr. Zharkova was kind enough to come on with Shawn and I and talk about what's going on with the grand solar minimums that Shawn and I have been talking about in the podcast here over since about 2018 and leading up to this 21-22 time frame where we're starting to head into now. She lays it out real nice and just shows a lot of great stuff. So this was also videoed. So if you go over to my YouTube channel at Moving Iron Podcast YouTube channel, you can see the video as well and all of the information that she has there as well. So hope you guys enjoy this. Shawn and I kind of lay out what's going on in each one of these podcasts. So again, a great honor to have Dr. Zharkova on here. And again, people talk about following the science. Well, here you go. It doesn't get more scientific than this. Hello, and welcome to Moving Iron Podcast. This is a special edition that Shawn Hackett and I did together where we interviewed Dr. Valentina Zharkova. And Dr. Zharkova is one of the leading researchers in the field of grand solar minimums, solar activity. She's got, as you heard earlier, she's got a laundry list of degrees that stack up to make her very, very much a well-rounded and well-renowned scientific author out there that's got a lot of great information about stuff. So we've got Shawn Hackett here with me, and he and I both interviewed Dr. Zharkova, and this is a two-part program that we put together here. And I think altogether we have about 120 minutes or so worth of information. So, Shawn, what's the best way that you would describe this part one here of Dr. Zharkova's interview?
I think part one, what she was trying to convey, and I think what we were trying to convey is why does the sun do what it does? How do we measure it? And how can we use modern day techniques and mathematics to project forward what solar activity will look like? And so it's really kind of an education on the sun and the mechanisms behind it, how we know what it's doing and how we can project what it will do. And so that's really the takeaway from this first this first part is kind of really getting an understanding of how the sun operates, what is a solar cycle, that sort of thing, so that when we talk about part two, people will have a framework to go by. So,
yeah. And the nice thing about this stuff is that this is not someone's opinion or whatever. This is all scientific data. That's peer-reviewed data. That's all in several scientific journals that's easy to find. That is all very peer-reviewed and by others that are in the astrophysics field, right? So this isn't something that just some person made up, and it is what it is. So I'm looking forward to this part one. I think I sat through it, and I learned a lot from this just because the fact of I have a very, 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 very high level understanding of what's going on. I don't have any of the technical backing to really, get the good feel for this, but Shawn does, and Shawn understands quite a bit what's going on there, and you learned quite a bit from it as well, didn't you, Shawn?
I really did. I mean, to see it through the mind of a physicist, and at the level she understands it, the level of understanding that I got from it was just tremendous. I mean, it was I thought extremely helpful, informative, and I walked away knowing, a lot more about what's really going on than I thought I did. So I hope your listeners, feel the same way when they watch part one.
Right on. Well, Shawn, I'm looking forward to this, and we will let part one roll, and we'll see you again in part two.
Sounds good. Thanks, Casey.
This is truly one of those opportunities in life that come along, and you don't necessarily get to have them that often. And I'm lucky to have one of the foremost researchers as far as sun cycles and those kind of things take place in here with us today. And before I introduce her, I want to introduce Shawn Hackett, which everyone knows. Shawn Hackett listens to the podcast. He's on every week, and we talk about what's going on in the commodity market. And he was the first person to bring this idea of the of grand solar minimums and how they affect the Earth and what we're running into here in 21 and 22 and what that might look like. So, Shawn, thanks for being on the podcast.
I'm honored. I'm really looking forward to the show.
Yep, me too. So, the guest of honor, Dr. Valentina Zharkova, is my guest here with Shawn Hackett and myself. And I reached out to Dr. Zharkova to bring her on to kind of give us a good understanding of what's going on here. And before the podcast came on, you heard what her background was and what that looked like. And as you can see, she's very well versed in all levels of physics and mathematics. So, Dr. Zharkova, thank you for being on the podcast.
It's my pleasure to speak with you and to answer your questions and educate the people if they're interested in the solar activity, its effect on the life on Earth.
Yeah, I think there's plenty of people interested in that, especially with the folks that we're talking with here. So, real quick, Dr. Zharkova, could you give us just a brief definition of what a solar minimum is and a grand solar minimum? What's the difference between the two?
Okay, let's first remember that the solar activity is defined still by number of sunspots which appear on the solar surface. And here I present these. They were discovered ages ago, first after invented telescope observed in 1609 on the sun, but also sunspots were observed visually on the disk. When you project the solar disk on the wall, if input white paper, you see these dark spots, and people put handwriting drawings and calculated them. So these are sunspots, dark spots on the sun. And it turned out that when you look at the sunspots, they do not appear randomly. They appear actually pretty regular with the period about 11 years. So they keep appearing somewhere in the plus minus 30 degrees of the solar, from the solar equator, and slowly moves during the solar cycle towards the equator. So basically what you see from this is the result of 400 years of sunspot observations. The blue things here, these are 11-year cycle, average number of sunspots, which people observe. So you can see that every 11 years, cycle goes from minimum to maximum, minimum, maximum. And this lasts until 1600, minimum, maximum. And from that, everyone can see that some cycles have larger number of sunspots on the solar disk, which are called modern maximum. It was somewhere in 1960, 1980. In some times, this solar maximum number of sunspots much lower, twice or more. Here, as you see in about 1800, It was Dalton minimum when the number of sunspots was about not exceeding 50, even during the maximum. And when you look backwards up to the mountain minimum, they went for about 60 years, from 1645 to 1715. Literally, there were no sunspots, or very little sunspot. And this is what Maunder call mountain minimum, and this is what we call grand solar minimum. But at that time, we didn't know how often this grand solar minimum occurs. But from the comparison, you see that. So these are 11-year cycles. The number of sunspots increasing during the maximum, decreasing during minimum. Then sun recuperates and starts the new cycle. And every 11 years, it changes. So what is the solar activity? If we look at the sun, what is happening at the bottom is minimum of solar activity. So basically, you don't have sunspots, and we don't have coronal mass ejection, don't have any activity on the sun. The magnetic field of the sun is very straightforward, and there's no activity in the solar atmosphere. The further you move in time, this is the cycle 23, 96 was minimum, 96, 97. The further you move to the maximum, which was 2001, you see that the solar atmosphere become burning. It is like a fire. Yeah, you see no any atmosphere, no any emission. And look at this 2001. It has a huge number of explosion of everything. This called solar activity increased. And obviously everything which is increased on the sun is emitted into the interplanetary space and comes to all the planets, including the Earth. So all these particles, all this energy, all these waves, they all come in towards us and disrupt our geomagnetic field and cause auroras and different kind of disruptions on the Earth. So this is what basically what is the solar activity, and why the sunspot cycle is pretty important, because we know that now we are the minimum of our cycle 25, so we're somewhere here, and the next 5 years we will be moving to its maximum. So the solar activity start increasing, but before that we had to add 282 days without sunspot at all, which marked that the minimum between cycle 24 and 25 was very long. Normally it takes a few months, maximum year, but it was very long minimum, which shown that there's no any activity, no sunspots. Literally, sun was spotless, was ideal sun, orange and beautiful. So this is the solar activity index, which shown you in these average sunspot numbers, and this is the description of the solar activity through average sunspot number every month. They produce it and they cover in every 11 years. Sometimes cycles last 10 years, sometimes 12 years, in average 11 years. On the top, the location of sunspots on the solar surface. So they start somewhere between plus minus 30 degrees northern hemisphere, southern. This is beginning of cycle. And then they slowly migrate toward the end of the cycle, slowly migrate to the equator, and then disappear or move to another cycle starts again. So
Dr. Zharkova?
Yes.
Doctor, why does this happen? Why does the sun just always putting out the same amount of, why does it fluctuate? What's the basis behind why the sun does
question.
This? Yeah.
This question is related to the magnetic field of the sun and so-called electromagnetic dynamo. So it turned out that the sunspots are not simply dark spots. They are foot points of the magnetic loops shown in here in this bit, which are embedded into the solar surface. So the loops are embedded, and when they appear, the roots looked as sunspots, and the loops are then produce you flares and all these brightenings which we see during the maximum. So why it is happening? This is, let me go through that. Here is action of electromagnetic dynamo. So the electromotive force at the bottom of Tucker line, it converts magnetic flux of magnetic loops into the magnetic field of the whole sun and vice versa. So using the magnetic field of the sun, this electromagnetic force creates magnetic loops at the bottom of Tucker line, or the bottom convective zone of the sun. And these loops, they are created during the minimum of solar activity. And then over the 5-6 years, these loops are traveling through the solar interior and appear on the solar surface at these loops, as I shown in the previous slide. But because the sun rotates, so the magnetic field of the sun is poloidal field. So from poloidal field, they create magnetic loops, which is toroidal field. So these loops appear on the sun, on the top, but because sun rotates not with the equal velocity in all latitudes, its equator rotates faster than poles, which means these loops which appear, they start being twisted. So the front part of equator, it moves quicker, and the loop started twisting and getting around the sun. So it started converting over the maximum. Toroidal field starts slowly converting back to the poloidal field. And this example shows you how the poloidal field of the sun acts. So if you forget about this toroidal field, these loops, and explain how the magnetic field of the sun acts. So this was solar minimum, northern polarity, southern polarity, and you see no loops on the open polarity, open magnetic fields. So this is what happened. Then these loops which are formed at the Tucker line very deeply inside the sun, they travel along the 4 or 5 years, and they start appearing on the solar surface. But because sun rotates, this loop become twisting, they become shifting, and this is what they form, kind of this structure, which is toroidal field. So this field much stronger than this poloidal, but what it does, it actually makes these loops migrate and carry this magnetic field. Southern polarity carries to the north and northern carries to the south. This is how it's done. So now this magnetic field from the loops is converted to the poloidal field, and it changes polarity. So when we came to the next minimum, the sunspots are carrying this magnetic field and change the polarity, help to change the polarity because of this dynamo machine.
So what you're saying is there's a period where the magnetic fields are offsetting each other that creates a lower magnetic field, and then there's a point where they are working together to increase the magnetic field that allows for sunspots to occur.
The sunspots occur during the minimum. The only magnetic field of the sun allows to appear where these loops can pop up on the surface. Right. So because the sun has it is acting, its density is about water. It has quite a solid magnetic field. So its magnetic field allows in which place sunspot can appear and how they can move.
Right.
This is what it does.
Okay.
And because of this, what you see during the maximum, the polarities are migrating. And in some years during maximum, your north and south pole could have the same polarity because the polarities are shifting. They're migrating from south to the north and from north to the south because of these loops, sunspots. They're helping to exchange toroidal and poloidal magnetic field. And this is how it happened during the solar maximum.
Okay.
Gotcha. Okay.
Okay. Right. So this is I have some very nice video which shows, if we can stop for a second, I can find this video to show how it works. Do you wish me to show the video?
That'd be great. Yeah.
Okay. Let me find the video.
Dr. Zharkova, when did you first start researching this subject matter?
When I was at the university at the age, I think 19, it was interesting. I was learning applied mathematics, and we had part of this course was astronomy, and they wanted us to do kind of labs and observations, and many observations were with the stars. You need to go at night and observe the stars, and I discovered that after 2 a.m. I stopped being human being. I'm getting asleep around the telescope. So after that, I decided if I need to do any astrophysics, it has to be the day star. It has to be the sun. It was literally my personal properties did not allow me to view. But nonetheless, it helped.
Yeah.
And I did my first master degree in some actually statistical analysis. I'll try to see where's my... Right. So this is how minimum solar activity, then you get this magnetic field appeared and form, you see they're twisting around the equator and form loops.
Right.
And loops then form. So this, how the loop are formed, this is because the toroidal magnetic field is twisted and they form these loops and sunspots occur there. This is how it happening.
Wow.
I can play it again if you wish.
Yeah, that'd be great.
This
That's
is
really
how
cool.
it looks like.
This is like when I'm watching the Science Network or whatever, and they're talking about the sun, and they're talking about solar spots and coronal
Wow, that is really cool.
masses and stuff
Yeah.
like that.
That's
Those blue
really neat.
that blue loop that I see on these, that's like the coronal mass ejections and all those different things that they're talking about, right?
Yes, exactly. This when they happen, when they come to the maximum, we started from minimum and stopped at the maximum. At maximum, this you have everywhere these loops and they produce all these ejections and everything. Only because you have different differential rotation. So this is called so-called alpha omega dynamo. So one thing is that the loops are appeared somewhere deep in the sun, and when they travel in, this is called alpha effect. And each depth, these loops are affected some different properties, buoyancy, the magnetic permittivity, and so on. But also, this is alpha effect. And omega effect, this is different differential rotation. So if your sun is occurred at the latitude 30 degrees, sun group, and other, for example, here, and the other part of the loop is at degree 25. So 25 will be try to move away further because sun rotates quicker. This is why it is shifting. This is why magnetic field is shifting because of omega effect. Okay.
So now we produce these sunspots. So why do we care?
Why do we care? Because when you produce the sunspots, what you do, you have this increase of solar activity around the sun, like you're looking here backwards. So what we got, the sun become burning, become a huge fireball. It was quiet, nothing else, only this slight race along the equator, and suddenly it become a huge fireballs. We have CMEs, we have increased solar wind coming towards us. We have explosion, eruption, and so on. And very often eruption can be angled towards the Earth, which produce strong geomagnetic storms and so on. So this is the energy which come to us. And when the eruption reaches the Earth, what is happening, basically, it penetrates through magnetic field of this Earth towards the Earth, and normally it penetrates from the poles. This is the easiest way for particles, but some very strong flares, they can actually make particles penetrate so deeply. Normally auroras, they cause aurora, these particles, and they happen in the northern latitudes, in Finland and Arctic Circle. But in 1989, it was very powerful flare in March 1989, and the eruption of particles was so strong that the particles actually penetrated toward the province of Canada and destroyed power stations. So whole province of Quebec province was 24 hours without power because solar particles destroyed power station. And the similar in 2003, we had a strong flares, Halloween flares, about 10 in 2003 on the sun. And the emission from these flares actually completely destroyed 2 Japanese satellites because they didn't. So when the particle go, they just pass through anything. They're very energetic. They need the speed of light, so nothing can protect them. So they go through the aerial. Normally a satellite has aerial to communicate with the Earth. If they didn't close the aerial when the particle come in, they literally, with the good Kalashnikov, they killed the aerial, basically. It stopped working because it completely destroyed. So these have 2 satellites disappeared. So this is why people, especially when we started the space era in 1970s, 80s, people realized that sun is not so quiet guy sitting. It produces all this violent hot X-ray, gamma rays. It produces all these cosmic solar energetic particles. And it turned out that, oh gosh, we need probably have to have protection from the sun, or at least to know when to close we have very developed satellite industry, and they want to know when to close these solar batteries so the particle can pass through and they open and work again. Because after Japanese lost their satellites, this is where space weather become industry. People started interested in the prediction of flares, or at least they know when flare happen. They know how long take the particle to travel toward the Earth or where the satellites are. So the Earth, the light travel 8 minutes, but the particles, even the speed of light, 200,000 kilometers per second, it takes some time, minutes, 30, 40 minutes, given the distance. So they have this time to close, allow particle pass, and then open again. So this is why it's two dual. We develop industry. It's not simply we develop in empty space. The space ignores us.
Is there a correlation between the strength of the solar cycle and how many of these strong flares you get, or is it indiscriminate to that?
Normally it is. The stronger the cycle, the more powerful flares we have.
Okay.
So it is.
So in a grand minimum, we should have less of these strong flare events, correct?
Yes. When we have grand minimum, we don't have flares at all. Like it was grand, so during the minimum, they basically not only didn't have sunspot. It means if they don't have sunspot, they don't have any flares,
right?
Any coronal mass ejection. And turned out it is not so bad thing for us, because when the sun stopped producing this emission, the Earth started freezing. Yeah. Because we are warming up from this nice radiation which come from the sun, from our central star.
Yeah.
So the sun acts like a microwave.
Well.
In essence, right? So it warms. It's intense. There's an intense moment where there's a ton of heat being put off, and then when it goes away, then that energy goes away, and therefore you get a cooling cycle of sorts.
Yes, what it says, we are so close. Again, I don't have this slide. I have in another presentation showing that, again, I can find it for you, that the sun is large star and the earth is tiny. So whatever comes from the sun, we always in the shining lights of the sun and its magnetic field. So we do not actually appreciate how much sun gives to us, but it gives everything, all energy resources, all fossil fuel. It's the sun. It's conversion of this of solar energy into this fuel, oil, gas, everything. It came from from transformation. What is on Earth after its decay, it transformed in something else. So whatever we have, all energy come from the sun. So we have to appreciate it.
Okay.
Outstanding.
We do. We appreciate the sun.
Yeah, I do like
Okay.
it. I dig it.
So this, if we appreciate it, this would, as I said, before 2015, people mentioned Mount the minimum, more or less like, oh, it was very difficult time.
Yeah.
But what was the problem? Despite we know this solar activity, like I shown here, it is very difficult to predict what will be the next cycle. So when we reach cycle 23 and people started predicting cycle 24, there were 150 predictions. And most of them saying the cycle 24 will be much stronger than the cycle 23.
Right.
Only a few of them, handful, about 3 or 5, saying the cycle will be lower, and they were ridiculed. When cycle 24 arrived, it turned out it became much weaker than cycle 23, which means that, and the people could not understand why it is. And not speaking that they can predict cycle when cycle already started.
Right.
I cannot predict now using this dynamo model. I can predict what will be cycle 26 or 27. What cycle 25 started, they now produce prediction what cycle 25 will be. But they couldn't do this when we started cycle 24. So it's still difficult to predict solar activity with a little bit more than 5 years time scale. This is why we looked that sunspots have magnetic field. We look the magnetic field of the sun. This is the this poloidal magnetic field of the sun, background field of the sun. If you look at this field, blue is northern polarity and yellow is southern polarity. You can see that actually polarities of the background field and features follow these butterfly diagrams which we've seen in sunspots. Do you see that? So this is not sunspot. This is background field, but you still see those butterfly cycle 21, then the butterfly next cycle 22,
Okay, yeah.
then butterfly cycle 23. This is happened in 2000. The guy built in 2005 this diagram, and this gave some idea. Okay, if they interlap toroidal and poloidal field by default because of dynamo model, they should transfer one to another. So who is the main guy? Where is this like a problem, egg and chicken? Who is the chicken and who is the egg?
Right. Yeah.
Background field or magnetic field of these magnetic loops?
Mhm.
So this is what we did investigation in 2008. We compared statistical and magnetic field, background field, which shown on the top, and the sunspot magnetic field shown on the bottom, because we detected the sunspot magnetic field using all modern techniques, digital techniques. So
Dr. Zharkova, you can actually measure the magnetic field of the sun fairly accurately. I mean, we're able to do that.
Yes, now we have sun is presented in CCD camera with the pixels.
Mhm.
And when you get these pixels, you can measure each magnitude and how many of those pixels in each sunspot. And this is at the bottom, shows you sunspots. We measure sunspot in every single day, and then the whole 11-year cycle, and we shown that this is the leading polarity. So we added the group, added all polarities, and now the leading polarity blue for sunspot in the northern hemisphere, and leading polarity southern in the southern hemisphere, which is opposite to the polarity of the background magnetic field. This is what we found. And we found some other things. We found that actually this poloidal field is like has upper hand. It allows when the sunspot can appear and when then can migrate. So this is what we found.
So your thesis was that you should have better predictive value focusing on this bigger data set from the magnetic field focus than on the more limited data set of just measuring the sunspot number.
Exactly. Having this digitized all the data, this is done from the full disk magnetic field on the top and from the sunspot, we discovered that area covered by sunspot is very, very tiny, small, and we have little data. While when we get magnetic field, we get full set of pixels, 1024 by 1024. So we have much more data and much more reliable data because they're more accurate. And this we thought, if we can start using this data instead of sunspots, we might be have better prediction of the solar activity. The idea was to predict solar activity for 11-year cycle, a bit longer time scale. This is why we decided to use background magnetic field.
Okay.
Okay. What we discovered when we look at this magnetic field, you look at this map. If you look at the sunspot, it is more or less like straight line, northern polarity, blue part on the top and orange at the bottom. But when you look at the background magnetic field, you see this big blue incorporations. So it looks like this, whatever magnetic field is, it's very polluted. It has many different waves. This is what we look. We try to reproduce it. Many people tried, they reproduce how it behaves, but it was difficult to use this field for prediction. And this came up, again, I'm a mathematician, and we look what the mathematical method can debug for us this magnetic field. Like we had white light. We never knew that white light consists of different wavelengths until someone guessed, put white light through the glass prism. And it turned out because of different diffraction law, suddenly white light became a rainbow. So you have from ultraviolet to the red. So, and each wavelength has a straight wavelength. It is nearly coherent wave. This is what prism is, an ideal thing shown. Very complicated white light doesn't have wavelength. It is white light. But suddenly you have all these wavelengths. We wanted this wavelength. We didn't know how to get it. The only mathematical tool which can do it for us is principal component analysis.
So you're saying that the mathematical equation in this case acted as the prism to differentiate and split out what was going on with the magnetic field.
Yes, exactly. We use covariance matrices and we try to classify these waves by the variance of data which contributes to them.
Mm-hmm.
So basically what we did, we found how much data from the whole data set from one day disk or 1 month disk or magnetic field in 1 year and 11-year, how much they contribute towards this particular vector. So we thought we will find one main principal component and we can say this is my major component and so on. We can see many. Principal component allows you to split your components into put them into order, ranking order. Highest variance, lower, lower, and lower. So on the left-hand side, we put variance in percentage. And here will be eigenvalues or own wavelengths of the oscillations. So it turned out this is what Sun's shown us. We couldn't guess that we don't have one principal component. The Sun's shown us two principal components. You see these two dots here.
Right.
Yep.
Two dots. And because it had two dots, altogether, one is 20%, another is 18%, in total 38% of variance of the whole data contribute to this principal component. It means if you convert variance is square of standard deviation, if you get square root of this one, you get 67% of data contributing to these two principal components.
So you're saying is that if you can focus on those two principal components and reduce the rest of it, that's how you're going to be able to predict the solar cycle going forward.
Yeah, exactly. So we decided to get rid for time being for these are later we discovered this principal component produced by dipole magnetic sources, north and south poles. Then you have quadruples, produce quadruple sources, sextuple, octuple, and so on. So we got rid of them for time being and decided let's concentrate on dipoles. Forget about others. Moreover, it is 67% by standard deviation. So it is pretty good distribution. If you look at any distribution, it's within plus minus 1 sigma. So it's fine. So this is what we look at. Just to show you, we got cross correlation. And this is what for dipole sources. You got dipole sources. We just got them, and this in paper 2012. We got here the quadruple sources, the sextuple and octuple. So we got them when you do cross correlation with them.
So this is the net result here of focusing on the main components and how you to predict future solar cycles.
Yeah, we didn't predict. Look only for the result on the left-hand side before this dashed line. So we didn't have it for time being. What we got, this blue and that line up to the year 2005, I think, 2006. So what we discovered that these two principal components, which we have, they actually follow very strict rules. These are magnetic waves, so these are magnetic field, right? So we assume these are magnetic waves, like in white light, one of them higher energy and the lower doesn't matter. But they are, during the minimum, if you look at that, the waves start, both waves start, one starts in southern hemisphere, somewhere in the 45 degree, another starts in the northern hemisphere. Both they move to the southern hemisphere and they meet, their amplitudes are close and they interact because they both in the southern hemisphere, they interact and produce maximum of solar activity. Then they move further. They move, the one which moved from the south moved to north and stays in the north, and the one which moved from the north moves to south. And then they put in the minimum when the waves are in opposite hemispheres, no activity. So what we discovered, for solar activity, we need these two waves to meet. On the same hemisphere.
On the same hemisphere, right.
Yeah,
and when they're in the opposite hemisphere, they kind of cancel each other out and the sunspots are not able to form.
Yes. And this what's happening. This is minimum. And then they meet in the southern hemisphere. And normally this hemisphere where they meet, it becomes more active. It's been notified by many scientists. One hemisphere always more active than other one, and always southern active in even cycles, and northern is active in odd cycles. So this is what we understood. This is what happened. Moreover, in some cycles, when you get if you have two maxima here, the maximum nearly coincide, but sometimes this maxima, like in this one, can be separated. Some cycles have double maximum, so-called Gnevishev law. So it explains you why you have double maximum, because they interfere here, but they still have another wave has maximum in there.
Did you take this data and go further backwards to see if it's still verified backwards?
Yes, I will do. Let me finish.
Oh, okay.
How we produced the right-hand side.
Hold on, Shawn. Hold on.
The right-hand side we do not have. So for time being, we didn't have the right-hand side predicted data. So what we found that the amplitude of these waves keep reducing.
Yeah.
But we wanted to know this data. And normally there are a few ways. You can use artificial intelligence, train neural network, and produce data on the right-hand side. You can use support vector analysis or some others. This artificial intelligence method, you can produce numbers, but it doesn't give you much power to predict. So what we did, we were lucky. We'd done this work 2010. We are preparing publication. At the same time, 2009, Schmidt and Lipton, they published their paper in 2009 about symbolic regression using Hamiltonian approach. This is very smart kind of artificial intelligence, how they try to extract analytical expressions from given curves.
So basically, you took some very, very smart mathematics and applied it to what you learned to be able to project outward what the solar cycle might look like.
Yeah, what we managed to discover that if we use the principal component, we can derive mathematical formula shown in here, F1 and F2 for each of the component, presenting series of 5 cosines, product of cosines, basically. It reproduces these two curves so nicely. I will show you in this, hold a sec, in here.
Use that same formula to figure out combine values. So,
Yeah.
So you're saying that equation was able to mimic what it was able to, I see the.
okay, so you're using that formula
to match
the lines there.
Gotcha.
Yeah, well, basically, we produce this 5 cosine product of cosines, and here with the straight line, this is what we produce from formula.
Okay.
And with the dash line, this is what we discover straight from the magnetic field, because while we were doing this, were about 6 or 7 years, the sun keep producing activity, so we can now test our formula on the real solar data. And we discovered this is accuracy about, and the oval shows you where we are when we publish the paper.
Yeah.
So the solid line is what your mathematical equation predicted. What the dotted line is what you
is actual.
Yeah, exactly. And you see the accuracy pretty high. When we counted, it's about, when you count the pixels, about 97%.
Wow.
So we produce this curve on the right-hand side, and now we produce it from simple calculation. So we didn't have artificial intelligence. We have formula. And I'll give the formula eventually to people to use it because it's perfect and everyone can use it. But what it does, we calculated in the first paper, this formula forward 3 cycles. And what we discovered in cycle 26, you will have minimum because your waves by default become in antiphase.
Yeah.
So it will be destructive interference because one wave goes to one hemisphere, another goes to another hemisphere. So this was
so so what you're saying in 2030, just based I'm just trying to comprehend your lines here.
Yes, 30.
There's going to be a greater minimum, like more of a grand solar minimum of that's going to have a bigger impact on the climate in 26 than in 25. Am I understanding that correctly?
Well, at that time we didn't know whether it will be effect on climate. We just wanted to understand what we got. So what we decided to look at, if you look at these curves, we thought, 2 curves is too many. No one would predict solar activity with 2 curves. So we needed to come back to that.
To the net.
to that curve, the bottom.
Yeah.
We
Gotcha.
added these two components and we got the summary curve. You see this one, the bottom.
Yep.
And it shows indeed the amplitude is decreasing. But what is amplitude meaning? So in order to understand what this amplitude means, we compared the modulus summary curve. So we thought we reflected the all southern polarity magnetic field back to the north and built kind of modulus summary curve. And on the top plot, the black is our modulus summary curve, and the red oscillation, this is the average sunspot number index, which we took straight from the from the table.
Yep.
And it shows that voila, our actually summary curve reflects the solar activity. It's a very good solar activity index. And if you put this now, the solar modulus summary curve to cycle 25 and 26, you see that the cycle 26 average sunspot number will be much lower, 60% lower than the cycle 24. So this is what, again, at that time we thought, oh, maybe this is only cycle 26. How the sun behaved before. But now we have a huge advantage because we have a formula.
Yeah.
If you have a formula, you can calculate the summary curve for 2000 years. And this is what we did. We did in 2015. This is the data we used. And this is the blue is the summary curve, which we calculated until 3200 and backwards to 1000.
So this blue line is your summary equation.
Yeah, that's your actual math.
It is my summary curve.
Okay, gotcha.
That formula.
It's a formula, right?
Yeah. And what we found that, first of all, we found that this minimum, there's a grand solar cycle. Definitely we see that cycle, in addition to 11-year cycle, we have another cycle about 350, 400 years, which repeats itself every 350, 400 years. And this is called, normally when you interfere waves, it's called beating effect. So two waves, if they have more or less close frequencies, but not equal, they start producing this big overlapping curve. If you know beating effect more frequently, you have when someone comes to tune your piano. The guy has a fork, and your piano is not tuned, for example, to the right note. So he put fork sound and put your piano sound, the string. And then he hears beats, 2, 3, whatever. And from the number of beats, he knows how much he needs to put the tension of the string to remove this beating effect and make frequency equal to that one in the fork.
So it's following a harmonics.
Basically, it follows straightforward theory of the waves. The only thing that we don't have engineer who can tune the sun. So the sun produces this beating effect.
Right.
Yeah.
Beating effect itself. But probably sun even doesn't know what is producing because it works tirelessly producing those waves with the regular heartbeat.
So looking at your summary summary curve, and the 350 to 400 year harmonic behavior, it is suggesting that we are moving into a grand solar, based upon that cycle.
We just entered the grand solar minimum.
We just entered into it.
Very lucky. We will observe it from the front seat. Yeah, we can't avoid it.
Based upon the other chart, it's really going to kick in like late 2020s into the early 2030s. That's when it's really going to kick in.
Yeah, and until early 40s.
Early 40s, right? Like that's going to be the heart of it. That'll be the heart of the grand solar.
Yeah, it's right.
Gotcha.
Mm-hmm.
And what can we, I guess, so while we're on that topic, I mean, what are we expecting then? Like, what are we expecting to have happen during that time frame?
Well, so if you're right about, let's say your summary equation curve is correct, which it looks like it is, what does that mean for our climate? What does that mean for growing food? Because because we're involved in agriculture, how does this impact the world's ability to grow stuff?
Yeah.
I'll skip these theory explanations and bring you what the effect for the Earth.
Okay.
You look backwards. So we have example of ground solar minimum, which happened 370 years ago during mountain minimum. So you look at these solar irradiance, it turned out during grand minimum, it was a reduction of solar irradiance by about 3 watt per square meters, if you see this left curve. And this led to the reduction of the terrestrial temperature to about up to 1 degree. It is in the, think about in Europe and England, they didn't do maps for others. But the other researchers, Schindel et al., they did surface temperature of Earth over the globe. They published in this Science in 2001. And they shown that somehow during mountain minimum, the temperature was mostly reduced in Northern Europe and Northern America. Obviously, there were not many stations in the southern hemisphere, but at that time, there was deep freeze in many rivers. Rivers were had ice, and ice scraped south from Arctics, and it was drop in temperature, and it was drop in ozone abundances. Why it is matter? It turned out that this is how the Earth temperature or Earth climate is affected. So we have the stable jet streams which run in from one part through the ocean or in the atmosphere to another. But when you get to the ground solar minimum, your magnetic field is strongly reduced, which means that your jet streamline becomes very wavy.
Why does that happen? Why?
Because less ozone will affect the atmospheric waves, the less radiation coming from the sun because sun activities drop first, and less magnetic field. Remember, magnetic field drops nearly to zero.
Right.
Which means that is nothing which can affect, which can cause the Earth magnetic field to do. So there's no force which suppress Earth magnetic field. So this is possibly what Earth does to its own planet if without the sun. So this, I don't know why. But what the guys said, they said that it is because of the ozone, it affects this line.
Sure.
It causes giant wiggles, jet streams, and this is what creates this anomaly and reduction of the temperature. This is what they said. It is not me.
Sure, sure.
Them.
Yeah.
And this is what we started observing now. We're observing now, it was snow last summer in Carpathian Mountains, observed Ukraine and Romania. It was early snow in Canada this year, September 20. In Oman, Arabia, in the January this year, it was -2 degrees and snow in Arabian part of the world, which never had snow, as far as we know, at least 150 years before. So this, again, there was snow in America, in British Columbia, very big snowstorm in November. And if you know, only yesterday, I found the snow in Africa desert on 8th December 2020. And this is the picture Guy put on the picture. Mm-hmm. Snow in Africa. Do you hear me? It is absurd, but this is the fact.
So from that one chart, what appears to be the agricultural areas that would be most impacted by a deep minimum would be the North America, Europe, yeah, and maybe northern Russia. Like that would be the heart of what areas would be most impacted. It would seem.
Yes, but at that time, there not many data were available in the southern hemisphere.
Yeah.
This is why.
Yeah.
Maybe it's not the real reflection. This is the lack of the data. Yes, yeah, right. Northern was affected, but we had a lot of observatories covered it.
Right.
In Australia, South Africa, South America, we didn't have this.
Yeah. So
we don't know what was it.
So so the southern hemisphere is a little more of an open box, which we're not really sure what the impact is.
Right. Yeah. but definitely affecting northern, and maybe it will be affecting southern.
Yeah.
So this would why people very interested. But definitely, you're correct. This will lead, if snow start falling in the unusual places, which means that we will have cold winters and summers. We will have increase of volcanic and earthquake activities. Which
Is that because of the magnetic field
reduction?
reduction?
Yes.
Gotcha.
Yes. And volcanic activity. Remember when we had volcano in Greenland?
Mhm.
All the flights were stopped because no one could fly. It was dark cloud, and basically it covers. So if you have clouds on the earth, it doesn't matter how active is sun, but with the clouds, the warmth from the sun will not come through to us. So if those clouds from the volcanic activity cover the earth, it will start cooling off, even doesn't matter what the sun does. So this would difficult times. And plus, of course, if we have this snow coming to deserts, very warm places, it will come snows to northern parts and will reduce the vegetation time. So each vegetable, each fruit, they need some particular time to get enough harvest.
Yeah, the growing seasons are going to shorten, which will make it harder to grow food at the level that we've been accustomed to. Yeah.
Yes,
Yeah.
and this is good. This would I have to say, someone told me that very entrepreneurial Chinese people, they're buying land in Africa because they realize that Africa will be the only land which can grow things, and they will make big businesses there.
Yeah.
So this is the thing.
So this explains, so kind of back to what you're talking about with the snows, the early snows and stuff like that. So here in Scottsbluff, we had snow. I'm pretty sure it was the Tuesday after Labor Day. I could be wrong on that, but it was within a week or so of that time frame. We had 102 degree day, 302 degree days ahead of that snowstorm, and then on a Tuesday, it dropped down to like 32 degrees, and we had snow, and we had some measurable snow actually, and then 3 days later, it was 85, 90 degrees again. So, I mean, is that the kind of weather patterns, obviously, that we could expect with these just huge swings in what we see happening as far as when you start going in between seasons, like between summer and spring, those kind of things?
Yes, exactly. And these grand solar minimum are not rare in the past. When you look backwards, it was Wolf minimum, which was somewhere between 1300 1280.
Right. So is the red actual?
Red is what people derived from biomass of the
sea ice
of trees.
Oh, tree analysis.
Yes, the carbon 14 and beryllium 10 analysis. This is what they
and the blue is
our summary curve.
Gotcha. Okay. Wow. Good chart.
If you look backwards, we extended it to 10,000 before Christ. We hit even Homeric minimum during the Roman Empire, when for 30 years they stopped the war because it was so cold during the Roman times. The Rangers could not fight. It was minus 30 and they were freezing, so they stopped the war at that period.
Yeah.
So this is what it says. Obviously, it is nothing unique. The Earth came through this grand solar minimum million times, as far as I see.
So I need clarification on something. So the blue line, that's your mathematical equation, that's your prediction, that's your formula. The red line is carbon 14, analysis of tree rings and those kind of things, and what you had. Yes. What is the spike? Why is the spike so high after the modern minimum?
What they were saying that it was again, it was their definition, how they assign number of isotopes to the increased solar radiance.
Gotcha.
Obviously, it always related to the intensity of the background radiation of cosmic rays,
Gotcha.
right?
Gotcha.
So what is happening, maybe the background radiation, in this case, I don't know why they increase so high. It is some increase in solar activity, but it's not as high as they shown. So there was some fluctuation in the background intensity of carbon-14 cosmic rays when they used. The similar problem comes with this bit of curve in here. We see we have Maunder, we have before Maunder minimum, and between Wolf and Maunder, it is maximum, it is ground solar cycle in our curve. But in their curve, they have this minimum, which called Spur minimum. And when you look whether it was the Spur minimum, in reality, we look at that, first of all, at that time when it was Spur minimum, this is when they have minimum and we don't have sunspots. But we use the sunspot visually observed by Chinese, and they put pretty well into our curve, apart from this particular location when it was Spur minimum. So we look, what was Aurora Borealis doing during Spur minimum? So this is the Spur minimum, and you see Aurora Borealis were highest at that time than ever before. This is the Maunder minimum, and this is after it. It was this strong Aurora Borealis. It means that a lot of particles coming through. So obviously it was maximum of solar activity and not minimum. Moreover, if you look at the temperature of the Earth, they restored the temperature. So this is the Spur minimum. Normally during the minimum, we know the temperature dropping down. In Maunder minimum, we had frozen rivers and everything. Mm-hmm. So if we had real minimum, temperature of the Earth shown with this dark red light should be dropping here. But here the temperature is increasing. You see that?
Yeah. Right. Yeah.
They published it. They didn't bother to put together why the temperature is increasing. It is increasing while the ice, the Arctic ice, is also increasing, while Antarctic ice is decreased. At that time, I mentioned that basically it is related that in 1280, somewhere here, it was a very strong explosion of supernova Vela Jr. at the latitude 55 degrees southern latitude. Because it was so deep south, it was not observed from the most of the Earth. And the south of the Earth, we didn't have many people observers, most of them in the north, so they didn't see it. They only restored this supernova later on because they found the remnant. It's still radiating with a huge intensity, much higher than other. And this supernova distance was 600 light years from the Milky Way, which, to tell you the difference, if it was 500 light years, actually the solar system would cease to exist. It kills everything. The explosion of supernova produces such intensity of cosmic rays that it would kill everything which is alive and it wouldn't exist. This is why people observe novas and supernovas just to see. Luckily, they're very far away. This was the only one which was close, which means that it was emitting a lot of cosmic rays, and intensity of this radiation was so high in the 13, 14 centuries that the background was very high. And this is why when people calculated solar irradiance in that time from the biomass, they use standard background, which is relevant what we have now, and not the one which they should use in the 14th century when there was supernova.
So what you're saying is that their methodology has some discrepancies because the cosmic ray flux, which is normally tied to the solar cycle, when you have supernovas, breaks down. And so there's a discrepancy in how they calculate it using the biomass.
No, cosmic rays coming not only from the solar from the sun, but they also come in from galaxy, from everywhere. Normally, the cosmic rays coming from the sun, they have much higher intensity, whatever comes from outside. In this particular case, in this few hundred years, 14, the intensity of cosmic rays coming from the galaxies is higher than the one which came from the sun.
Gotcha.
Yeah.
This is the one.
So that distorted it a little. That distorted the data.
Yes, this is distorted by about 200 years. Basically, what they were measured should be going to the the minimum, but it's left in there. It's exactly about 200 years. The guy who invented this method, Libby, he actually, in a few papers, he explored this. He didn't speak about this particular, but he warned about this caveat deriving the age. So this is what.
Gotcha.
Okay.
Yeah. Yep.
Any questions further? Return to this curve. So basically, what it says that nothing out of usual with the ground solar minimum. If previous people survived, Romans survived, medieval people survived, we can survive it. But it came very handy. We know the temperature has been increasing since the minimum. So maybe it will come handy, giving us time to recuperate and decide why the temperature is increasing while it is start reducing, and we need to think how to.
So is your expectation that we would drop a full degree, like what happened in the Maunder minimum? Is that a realistic expectation?
No, I didn't do calculations.
No, but I'm saying though it said that the Maunder that the temperatures drop a degree. Is that what that chart showed?
Yeah, about 1 degree. If you look at that, where we are over here. Yeah, so if you look at that, but it could be somewhere between this and Dalton minimum, half degree. So there were some. I believe it will be more like this one. Some people argue they will be more like that, half degrees. But half degree, it is not little. It is average. It means that it will be fluctuating, some increase, some decrease. But if you get a little bit less heat, the temperature will be decreasing. And half degree maybe in Africa will be nice and fresh. But half degree in the northern, it can be quite snowy and minus frost.
Yeah.
So is that because, so when I hear something like the whole global warming thing and what you're talking about here, that we're going to increase the temperature by 1 degree or 2 degree or decrease 1 degree or 2 degrees, whatever it is. Does that have to do with the fact of how the sun sets at 23.5 degrees, or the earth sets at 23 and a third degrees or whatever it is on the axis, and the way that energy hits is going to be greatly decreased in the north and more towards the equator, obviously, where it gets constant direct hit. But is it because of the axis of the earth? Is that why it's such a dramatic swing in the north and the south?
No one knows. We will be learning in the next 30 years. This is the first time we have a chance to look what is happening during ground solar minimum. But if you look, currently the temperature is increased compared to ground solar minimum. So if it will be decreased by 1 degree, it basically comes back to this level, 0. Right. So it will not be as bad as during the minimum, because already temperature is decreased by 1.4 degrees. So it will decrease. You see this red thing increasing? Yeah. It will decrease toward here somewhere. So it will not be as bad as it was during the minimum, but still will be reduced temperature. So it will be a bit cooler.
Okay. So I'm going to ask you a question, and it's the elephant in the room. I think most people listen to this. How come it took Shawn to call me in 2018 and explain this to me, and for me to have to do a Google search on grand solar minimum before I figured out what it was? And that this is not, obviously, this is mathematical theory all combined into one thing to give you this data set, and you're using all these different things. Why is it this such a hard to find thing? Why is this not something that's more openly talked about in the mainstream media?
There are a few things about it. First of all, from 1980, they put forward this global warming, and solar physicists said that, all right, solar activity is stochastic, forget about it. It gives you standard heating, and this is maximum what it gives. So they disregarded the sun, and they don't want to get it back into the equation. So this is possibly one thing. And another thing is possibly some kind of misogynism. This the people who do this prediction of solar activity mostly are male, and they feel offended that two of us who discovered this were female. And I know that the guy, Mr. Soskin, he was chasing Elena Popova in Moscow very badly, and so this would probably another thing would put them out. I don't know.
Yeah.
I can't find the explanation. I thought it is you give the discovery to the world and they're happy. I'm happy to share even the formula. I didn't show the formula yet. I have all the coefficients. We wanted to get the full results, a few publications, and then we give it to the world. But I was ready to teach during the meeting, and they refuse to get teaching. They say, we know everything. And they put Mr. Soskin, after each paper we published, he put objections. So he put objections after the paper we published in Scientific Report 2015, we needed to answer. Then we published paper in journal Atmospheric and Solar Terrestrial Physics, Popova, we included quadruple waves. He again put a nasty thing. We needed to write answer. If you look at my website, you'll find that in the same issue, we answered every single point. This is where I came up with this nice prism and explaining what is principal component. We split into the wavelength to explain, because you say you can't get exact formula only from 3 cycles. I said, no, you can't, because it doesn't matter where you put white light. If you have a prism, you still have the rainbow on the other side. So if you use, we tried apply this principal component on a single cycle, on combination of 2 cycles in any, and 3 cycles, and we get the same eigenvalues all the time.
Email password.
Okay. So that makes good sense. So, Dr. Zharkova, this is absolutely amazing stuff that you have here, and I am absolutely honored that you were on the show here.
It gave some understanding, catching up what it is.
Yeah, absolutely. And, so I understand it better than I did with all the stuff I've read, and in the context that you put the stuff in during the show is going to help me understand quite a bit of the other stuff that I've been reading, and so I'm definitely going to be able to have a better thing. But like you said, we've got a front seat to history over the next 10 years and what that's going to look like, and it will be interesting to watch how the theories of global warming change over the next 10 years, especially with, the data that you laid out there, all the stuff absolutely fluctuate or absolutely happened the way historical data showed based on your stuff. So, it all lined up. Everything, if it was that far off and that wrong and this thing else, you would have had a hockey stick someplace, right? It'd have been a curve that you wouldn't have seen before. So
this is what sun's shown us. This is not what we invented.
Mm-hmm.
Now they're more and more inclined. More people now put in that, all right, there are dipole waves and there are 2 layers. They start putting, they forget to refer to our papers. I need to remind them 5 years later, but it takes a while. Obviously, it takes a while to digest it. So we were pioneers. We go through, and now we say, oh, we knew this, everything. We knew this in advance. We knew this 5 years ago as well. I said, why didn't you say Well, it's questioned.
Right, exactly right.
So
Well,
we will see. But at
yeah.
least in addition to global warming, we have something. Sun is on our side. It gives us time. I believe it will give us time to recuperate, and have this temperature reduced will allow us to evaluate what is happening and prepare for it.
Well, Shawn, do you have anything else you want to add?
Have you ever done any work, Dr. Zharkova, with the relation with sea surface temperatures at all with the oceans? And
I only use someone else's work, but since we published the papers, people voluntarily send me the papers presentations. So
sure.
I'm now much more aware of what people do. So if I even don't do, but I know what other people do because I have all the presentation, I'm in contact. It become much more popular than you might think.
Yeah.
The only thing that they try to suppress, those people who talk about anthropogenic global warming, they try to suppress even idea that the sun will reduce the temperature.
Right.
This is why it is so difficult. People know the sun will reduce the temperature. Sun knows, but they reject.
Well, I can tell you that NASA used to put out all kinds of work 30, 40 years ago about how important the sun was to the climate. And then all of a sudden, the last 20 years, they say it's not a factor, but they used to always say it was a factor. So
exactly.
So it's very interesting.
It appeared in this in NASA stuff list, and they put in this nonsense forward.
Yeah. I know we didn't talk about the CO2 angle on this particular interview, but what you talked about yesterday on the CO2 and why it really that would be a fun conversation to have.
We can discuss it in the next round of interviews.
I think that would be a great set.
Okay.
I think that would be a great discussion. Now that we have a really good understanding of sun and how it works and how you've been able to predict and all, but to go over the CO2 aspect of it and why it really can't be what everyone says is, that would be really, I think, an outstanding second program.
I'm happy to look through materials of all my friends and compare. We also did some work. We got independently again with this summary curve. We calculated backwards to 120,000 years, and we discovered some oscillations of the baseline, which we linked to this climate variation. But we will discuss it in later. What I want to say that with this ground solar minimum and the beating effect with what we approaching, we understood that the sun will live long enough, given the whole humankind 4.5 billion years, because its heartbeat is pretty stable. So what we have in sun is not stochastic. It's very well defined. It produces these nice waves as it should be. Its heartbeat is perfect.
Yeah.
The only problem is we have beating effect because we don't have engineer who can feed the sun and feed these beats. So this is what we have. It gives you good reassurance that, okay, we have enough years, and then who knows, we can go to another Milky Way by that time in 4.5 billion years.
I don't think I'll be around 4.5 billion years from now, but that's just my guess. But if you can figure out how to live 4.5 billion years, if you can let Casey and I know, we'd be very interested.
I hope to live for another 20 years. That's the minimum. I'm not that ambitious.
I think I'm good, Casey. I think that was a really good program. Really, really good program. So
okay. I hope your readers to find this discussion stimulating.
Oh, they will. Trust me.
Okay, thank you very much.
All right, so
thank you, Dr. Zharkova. It was fantastic. Fantastic. Thank you.
Dr. Zharkova, thank you so much for being on the podcast, and hope you and your family have a great Merry Christmas and enjoy the London Christmas.
Cheers. Okay, thank you.
Okay,
Bye-bye.
cheers. Thank you.
Moving higher in the 21st century. Hard-working people working hard for you and me. Moving higher, time and time again. Through the years you'll find us here.